Hey there, all you cool cats and kittens. I haven't actually seen Tiger King, but I've heard that that's how good old Carol Baskins talks. So hey there, all you cool cats and kittens. Welcome to episode 18 of Math 141 Summer 2020. Not Carol here, but as always, your boy Bailey. We are on section 5.6 today, and we will be reading between the curves. I hope that you get the joke today. The joke is like reading between the lines, but we're between the curves. Get it? Because we're gonna be finding the area between curves. Oh my gosh, okay, I think I'm funny. So 5.6, in addition to finding the area between curves, we look at the definite integral substitution method. So in the last two sections, in the last video, we looked at how we can use the substitution method, otherwise known as U-substitution, to solve indefinite integrals. And we also learned how to solve definite integrals using the fundamental theorem of calculus. So what we're going to do today is we're going to put those two things together and also see this geometric application to see how this notion of a definite integral is reflected in terms of the area between two curves. We started last time finding the area underneath a specific function, and now we're going to generalize that a little bit more. So without further ado, let us begin to some problems. Sorry for that noise. That was uncomfortable. My paper was rubbing against other paper. The first problem from the homework I would like to do, this is a relatively short homework assignment, only I think 13 problems. I would like to get done 6 of them here. That would be fantastic for both me and you. That's almost half. But as always, we'll see how things go, because I've been getting very excited and going a bit over recently. Last time I think was right on the dot at an hour, but there were a few 75-minuters before that. So the integral which we will be evaluating here is negative 2 cosine squared x times sine of x dx. There are a few problems in a row that ask us to use substitution to evaluate integrals with sines and cosines. The technique which we're going to use here is going to be basically the same technique which you're going to want to use for all of those problems. And in particular, the substitution which we're going to make is going to be very similar. So big picture, whenever we make a U substitution, we can't always do it this nicely, but we want to pick something for U, such that du is already present. Right, that's ideal. Again, as we saw last time, that isn't always going to be the case, and things don't always work out that nicely. But whenever possible, we would love to do something like this. So whenever I look at this problem, well, there are two things that I see, two possible substitutions that would make perfect sense. One possible substitution, in fact, I'll write them both down, and we'll go through both of them and see how they go. One possible substitution would be u equals cosine of x. In that case, du becomes negative sine of x dx. Alternatively, let me put the line in the middle as black to differentiate. Alternatively, we could go with u equals sine of x, in which case du is cosine of x dx. In both of these cases, we see that we have the derivatives floating around, right? The derivative of cosine is negative sine, and would you look at that, I've already got a sine here. We can also move that negative sign, right? So we do already have that derivative. And if we choose u equals sine of x, well, we already have a du. So we're already going to be in good shape there. However, so in some sense, both of these could probably be made to work. However, I argue that one of them in this case is in fact noticeably easier than the other. So let's go ahead and let's use this second substitution, and let's just see what happens if I make this second substitution, okay? So I'm going to keep writing in green. No, I'll just extend it. Yeah, I'll just keep going in this right-hand column. So if I try and make this substitution, okay, shoot. Well, okay, there are two ways of doing this with the bounds. For now, we're going to ignore the bounds and just look at the integral itself. Okay, so if I were to do that, then this integral, well, it looks like I'm going to have minus 2, and then cosine of x dx. Well, I have cosine squared here, so this would be, what, negative 2 du squared times sine of x. And I guess I should have, du. See, this is weird because I've got this du, and I'm trying to square my du because this is cosine squared x. And so that's why this substitution over here on the right is actually not really going to work for us. Maybe I won't do that. Let me just cross out this du squared here. That's what makes this really problematic. Having a du squared doesn't really make sense. Having a u squared, that makes perfect sense because u is just a variable. But having du squared, that would be like if in my integral I had dx, which wouldn't make a ton of sense. So we're actually going to ditch this substitution on the left, and we are going to go with the on the right, and we are going to go with the substitution here on the left. Okay, so this is the substitution which we're going to make. Now, from here, whenever we are doing a substitution on a definite integral, from there are two ways of proceeding. It does not matter which way you go, so long as you make your mind up, and then, how do I say this? Once you make your decision, you have to stick to it, okay? So the first thing that we can do is we can change our bounds of integration. So remember, those are just the bounds of integration are just the things that are like from A to B. It's just these things, blah, blah, blah. Okay, so the bounds of integration are just the thing at the top and bottom. And the way that we do that is by subbing in, subbing our bounds into the u formula for x. So in this case, what we're going to find, if we go ahead and do it this way, okay, well then my upper bound it was pi originally, right? If we look at our integral, our upper bound is pi, but we're going to replace it with u equals, we're going to replace it with cosine of pi because that was our formula for u here. So our upper bound, instead of being pi, it is now cosine of pi, or negative 1. Our lower bound, similarly, and this is another one of those situations where if you don't want to write all of this out, that is perfectly fine. So long as you make the substitution, okay, it's not a huge deal to me if you write it out this explicitly, or if you just make the change, that is perfectly fine with me. So our lower bound then, it was 0, so now it's going to become cosine of 0. Okay, to reiterate, all I'm doing is I'm plugging in these bounds, 0 and pi, into our formula which we formed for u. That is how we get our new bounds. So now our integral is going to look like the integral from our lower bound. This, we have to be careful. We're used to, usually, if I have the bounds from negative 1 to 1, negative 1 will be on bottom and 1 will be on top. However, since pi was on top, we still have to be consistent, and negative 1 goes on top now. Okay? So now let's go through and make our substitutions. Well, I've still got that negative 2. In fact, why don't I pull that negative 2 out front? Okay, remember, I can always pull a constant multiple out front of an integral. So I pulled this negative 2 out front. Cosine squared is now, that is just u squared. So I have a u squared. And now sine of x, well, sine of x dx, I can see from this line, from the du equals negative sine of x dx, If I multiply that by -1, then I see that negative du equals sine of x dx. Right? So I replace then sine of x dx with negative du. So times minus du. Okay? So now we've successfully translated into the language of u's. And let me just rewrite a little bit more. So I can adjust this. I can bring this negative out front. Okay, I can bring the negative with the du out front to make this just a positive 2 integral from 1 to -1 u squared du. But now you'll have to excuse me. I'm going to introduce another negative because I'm going to change my bounds to go from -1 to +1. Okay, so let me emphasize that I've made that change. Okay, so whenever I flip the bounds like this, we introduce a negative sign. Okay, so that's why I've introduced this negative here. And so now I have u squared du. You do not need to flip the bounds. However, like I said, I'm used to having the smaller bound on the lower end. So for me, this makes it more natural. But theoretically, if you stuck with it and followed through consistently, you would be just fine. If you did not make that change. Okay, so now I'm going to integrate. So I've got this -2. I'm going to come over here to give myself more space. So I've got -2 out front. U squared, well, I raise the exponent by 1, divide by my new exponent, so u cubed over 3. And I'm evaluating this from -1 to 1. So I substitute in -2. So I've got -2, and I'm going to substitute in, so I'm going to get 1 cubed over 3 minus, I always subtract out whatever I get when I plug in the lower bound. Okay, and then I plug in -1. Okay. And now I have -2, 1/3. Let's see, it looks like I've got minus a minus 1/3, so that's going to be plus 1/3. And it looks like this comes out to -4/3. So that's the first way of doing a u substitution on a definite integral. Okay, what we did was we changed our bounds of integration. Okay, and we substituted in our bounds into our formula for u in order to make that change. Notice that at the end, notice we never translated back to x at the end. We never translated, and no, that is not a mistake. Translated back to x. Okay. This is okay when you have a definite integral. This is okay if you change your bounds. Okay, this is okay if you change your bounds on a definite integral. Okay, so let me emphasize that, on a definite integral. Okay, remember, definite integral just means that we have bounds. In this case, for example, we switched them to 1 and -1. Okay, once we adjust our bounds by plugging them in to our formula for u, we've already taken care of everything that we need to. So then we can go ahead and integrate and plug and chug. Now, the second method of doing this, of doing a u substitution on a definite integral, is the following. How do I write this? Because the textbook kind of explains it one way. I'm used to writing it a different way. So we can leave our bounds alone and sub back in for x before evaluating. And I'll explain what I mean here. We'll go ahead and do this problem this way as well. Okay, now the textbook writes it slightly different. I'm not sure if Mackenzie wrote it slightly differently in her video, but in fact, that might be a good thing so you can see another perspective. So the way that I write this is what I'm going to do is I'm going to again make my substitutions. Okay, so what I'm going to do, my integrand, so my integrand here became -2 with the u squared negative du. Okay, so I'm going to go ahead and copy that down. So I've had my -2 out front, and then we had a u squared times a negative du. But I'm going to leave my bounds alone. Okay, I'm going to change the color here to make that clear. And I'm going to write x equals 0 to x equals pi. Notice how in here, and you don't have to do this, this is just me keeping track of things. Notice that I'm writing x equals 0, x equals pi, not just 0 to pi. That helps me remember that these are x values for bounds. These are not u values. So it reminds me, oh, later on, I'm going to need to shift back to x's, okay? So then we integrate like normal. Okay, I'm going to go ahead and skip a step here because we already got to, I'm going to go ahead and take us to this step here. Okay, I'm going to go ahead and take us there where we had, because that everything until there is going to be the same. Okay, so this becomes, we have a -2, and then I have u cubed over 3 evaluated from x equals 0 to x equals pi. Now, I'm going to sub back in with x. Okay, so this is going to become now -2. Well, u, we said is, what is u? U is cosine of x. So I'm going to have -2 cosine of x cubed over 3. And now I'm going to go ahead and drop the x equals because I'm already back in terms of x, so there's no need for that anymore. And now we're going to integrate, or we're going to evaluate just like we did before. Cosine cubed of pi over 3 minus cosine cubed of 0 over 3. And let me see what this comes out to, -2. Well, cosine cubed of pi, that's -1. I'm thinking that I made a typo because I'm thinking that I'm not going to get the same answer here. But we will double check that in just a minute. That's not a big deal. That's clearly just me making a small mistake. So -1/3, and then cosine of 0 is 1, so that's -1 over 3. And so this gives me +4/3. And I think in the first one we got negative, so that's just a typo. Hang on a minute here. Let me, how did I do that? Oh, okay. So everything was not the same, excuse me. This negative sign should not be here. Should not be here. So it should be negative, that should be positive, positive. So my final answer should be negative. The reason, and I was lazy and I should have just gone through and done it all. The reason that we had the extra negative sign, the first way that we did it, we introduced this negative sign here whenever we flipped the bounds, right? We introduced this extra negative sign. However, down here, we never flipped our bounds. So that's why that's why whenever I jumped straight to the yellow box step here, that's why whenever I jumped straight there, I had an extra negative sign. So my bad, but I hope the general technique makes sense. Okay, so there are two ways of doing this. You can either change your bounds of integration and put them in terms of u, or you can leave your bounds alone, but then make sure that you substitute back in for x before you evaluate. That is important. Before you evaluate. Okay? So before you start plugging in the numbers and doing some algebra at the end. Okay, so that was about 20 minutes just to get to this point. However, I think it was time well spent because I think it is very important to see and understand both of those methods. Now, like I said, this type of problem where we have sines and cosines and we make one of these substitutions, either u equals cosine or u equals sine, I think that you will find that helpful for a couple of other problems in this homework assignment. The next problem, which I do not believe will take as long. In this next problem, I'm not going to show both ways. I'm just going to show one way, which will probably be way A. That's generally what I do. But again, whatever makes you comfortable. I used to be a big believer in way B because that's what was originally taught to me. But the more that I used the second way, or the first way, I decided that was easier. For x dx. All right. So remember the little tip which we gave at the beginning last time. We want to pick a for whatever we pick our u to be. We would love to pick something whenever possible so that our derivative du is already present. It's already floating around somewhere. Well, if I look at this problem, what I notice is that if I let u be the natural log of x, then du is going to be 1 over x dx. And you don't need to do this, but if you can't see right away, notice, well, first of all, let me go ahead and pull a 4 out. But notice then that this is just ln of x cubed, oh, not ln of 3, ln of x cubed, times 1 over x dx. So this becomes, okay, well, let me change my bounds real quick. So bounds, so upper, I'm just going to be lazy. Upper goes from 11 to ln of 11. Right, so my upper bound, I'm going to take 11 and plug it into my u formula. And lower is 1 goes to ln of 1. So I'm going to leave ln of 11 alone because I have no idea what ln of 11 is. It's some hideous number, I'm sure. But ln of 1, in fact, we do know is 0. So I'm going to go ahead and make that change. Okay, remember, ln of 1 is 0 because e to the 0 equals 1. That's why that works. That would be a good thing to review if that doesn't make sense to you. Okay? It's definitely tricky. I'm not saying it's easy, but you should have a good understanding of it at least come exam time. So make sure that you feel comfortable with that identity. Okay, so now my integral becomes the integral from 0 to ln of 11. ln of x is u, so this becomes u cubed. And then 1 over x dx is just du. The other comment which I will make regarding how we can choose our u, so it is nice that we see our derivative, our du, already floating around. The other good thing, though, the other thing that makes ln of x an attractive choice here is that I don't know what the integral of ln of x is. The integral of ln of x is actually quite challenging. It's quite tricky. So if we make the substitution, u equals ln of x, we take this really ugly, complicated thing, right? I think you would agree that I don't want to integrate ln of x cubed. That looks gross, right? So if I make this substitution, I can make my integration a whole lot easier. So that's the other way that can help motivate your choice of u, can be turning something ugly into something cute. All right, well, let's go ahead and complete this bad boy. So that becomes 4 times, well, u cubed. Whenever I integrate that, I'm going to raise the exponent by 1, divide by my new exponent, and then I'm going to evaluate that from 0 to ln of 11. All right, so then I'm going to plug in my bounds, and I get 4 times ln to the 4th of 11 over 4 minus 0 to the 4th over 4. This second fraction is, of course, just 0. In this first fraction, I get 4's canceling, so it looks like I just have ln. Maybe I should write it this, no. Yeah, I'll write it this way, ln of 11 to the 4th. These are the same two things. I'll write it the other way to make it more clear. ln of 11 to the 4th. So that gives us our solution. See, I told you that one wouldn't take as long. With natural logs, remember their derivative is 1 over x. So a lot of times you like to do that whenever you see something with x's in the denominator of a fraction. Okay? Wonderful. Next up on today's agenda is problem 6. Let me hydrate real quick. All right, problem 6. Ooh, this is one of my favorites. I absolutely adore this problem. Use the substitution method to evaluate the integral. Okay, and our integral this time, and it's going to look ugly, I understand, but bear with me here. Negative ln root 3 over 3 is our lower bound, which kind of ugly, but we'll deal with it. The upper bound is nice and simple, it's just 0. And then the integrand is e to the x over 1 plus e to the 2x dx. Okay. So why on earth, Bailey, why the heck do you adore this problem? It looks so ugly to me. Wow. Well, here's what I notice. And again, this isn't something I would expect you to notice the first time, but the more of these that you start to do, you start to pick up on these cute little things. Well, if I imagine that I'll just call it v, because I don't want to make this an official u substitution quite yet. If I let e to the x be v, then e to the 2x is going to be v squared, right? E to the 2x is just e to the x squared. So this it sort of looks like, if you squint your eyes enough, it sort of looks like I might get something like 1 over 1 plus v squared. Right? I do have a v on top, not a 1. But it sort of looks like I might be able to get something like this. That would be great, because we know what the integral of 1 over 1 plus v squared is. That's arctangent. Okay, that's one that we should know. So it would be great if I could get something in this form. So that's what motivates my choice of u here. And as you may have guessed, I'm going to let u be e to the x. So then du is going to be e to the x dx, right? The derivative of e to the x is just e to the x. And I'm actually going to rewrite the second equation as du over e to the x equals dx. Okay? Now let me also address my bounds. So my upper bound, it was 0. Now it's going to be e to the 0. Well, e to the 0, that's very cute. That's just a 1. My lower bound, oh boy, this is the one that's going to be super fun. I have negative ln of root 3 over 3. Oh, okay, Bailey, we can do this. So that's going to become e to the negative ln of root 3 over 3. Okay. Well, let me see. What else can I do here? How can I simplify this? That's got to be simplifiable, right? Well, it looks like this is e. Yeah, so I can rewrite this as e to the ln of root 3 over 3 to the negative first power. Okay, I brought this negative sign. This is a negative 1. So I brought it into the exponent because of natural logs. That's a thing we can do. And now this is e to the ln of, well, the negative first power. That just means flip it. 3 over root 3. And now I'm going to use the fact that e to the ln of a just equals a. Okay, this is just a general fact. So this is just 3 over root 3. Whew, see, that wasn't terrible, right? I mean, yeah, it was cute. It was pretty cute. So now let's go back to my integral. What color was I writing my integral in? I was writing it in this goldish color I've chosen for today. I always choose a 6th color for the day from that large panel of colors to mix things up a little bit. So now my integral becomes the following. My upper bound, we said, is now a 1. My lower bound is now 3 over root 3. We again have a situation where my lower bound is bigger than my upper bound, but oh well, we might just leave it in this case because there's already so much going on. Don't want to overcomplicate things. Okay. Well, e to the x is u, right? I'm going to go ahead and erase these v things now because that might just make things more confusing. So now e to the x, my numerator is e to the x. E to the x. The denominator is 1 plus, remember, e to the 2x is just e to the x squared. So that's going to be 1. Why did I write e to the x? That's supposed to be a u now. That was the whole point. U over 1 plus u squared. Okay, and now I need to substitute for dx. Well, dx is equal to du over e to the x. So I'm going to multiply this. Oh, and I should actually further rewrite this as du over u. Okay, so dx equals du over e to the x, but e to the x is just u, right? So this really is just du over u equals dx. So then I'm going to make that substitution, du over u, so times du over u. And now this becomes the integral from 3 over root 3 to 1. Well, would you look at that? I've got canceling u's. And so I just have 1 over 1 plus u squared. That looks like a w, but it's a u. 1 plus u squared du. And this, as the prophecy foretold, I don't think I wrote it, but it looks just like we kind of thought it might. And so this is arctangent of u, evaluated from 3 over root 3 to 1. Okay, so now we're going to use our arctangent knowledge. So arctangent of 1 is going to be pi over 4. Remember, arctangent is asking where in the interval negative pi over 2 to positive pi over 2. I guess I should write a quick reminder of this. Arctan x equals where in pi over 2 less than or equal, where in, I'll just write it as an interval. Where in the interval negative pi over 2, positive pi over 2 is tangent equal to x. That's what arctangent of x is asking. Okay. So where in this interval is tangent equal to 1? Well, that is at pi over 4. Where in this interval is tangent equal to 3 over root 3? Well, it might help to notice that 3 over root 3 just equals root 3. And tangent is going to be root 3. Let me see. Well, at pi over 3, I have sine is root 3 over 2, cosine is 1/2. So yeah, tangent is root 3 at pi over 3. And so this becomes, let me see, that's 3 pi over 12 minus 4 pi over 12. I believe the answer should be negative pi over 12. I'm going to actually check this one real quick because I just want to be sure. And my math lab says nice work. Thank you, my math lab. I needed that. Okay. All right. Very, very good. I believe that concludes our integration, the first kind of half of this video. Yeah, the integration by substitution ones. Although we might need to do that in these later problems, we'll see. But the later problems, we are going to look at finding area between two curves. So we're going to start with problem 9, which says find the total area of the shaded region bounded by the following curves. Now this problem is going to be slightly trickier than perhaps the most basic examples. So I'm kind of assuming that you have at least a very basic kind of even if you haven't really done these types of problems before. I hope that you at least have the basic ideas down from either the textbook or the video, or Mackenzie's videos to this point. So I hope, of course, that it will be accessible, but I might have to, yeah, we'll see. Okay, so this is the first function, and this function here is, I'm quite proud of that. It's quite a good drawing. These are pretty precise drawings. I'm going to label them and everything because this is what's given on the screen. X equals 36y squared minus 12y cubed. The other function then looks like this. It looks like that goes out further. Like this, and it crosses right here. It crosses like here. I'm gonna make that point really big. That's what you do, is you make your point bigger so that your graph goes through it. And I'm gonna make the origin very big as well. Okay, and this graph is given by x equals 4y squared minus 12y. So whenever we do these problems, usually we're finding area between curves of the form y equals some function of x. Here, however, we are doing things in terms of x where we're looking at x as a function of y, right? I suppose, no, in fact, I was going to say we could go through and solve for y, but actually we couldn't in this case because neither one of these is a function of x, which you can check with the vertical line test. So what we're going to do is you're basically going to imagine rotating the plane. So imagine, I don't know if rotating it is the right word. So whenever we integrate stuff, whenever we find the area between stuff like this, oh, no. Okay, if this top function is f of x and this lower function is g of x, to find that area, we would integrate f of x minus g of x dx over the appropriate interval, right? In fact, let's go ahead and label these intersection points A and B. Right, so this is how we would find the area in that case. Here, whenever we're sideways like this and we're instead looking at x as a function of y, the top function, quote, is the function to the right. The function to the right over the interval. Okay, over the appropriate interval. So in this case, the top function, the thing that's playing the role of kind of what we're used to seeing as the top function, is this function x equals 36y squared minus 12y cubed, okay? Because as you can see over this interval, it's on the right. We're over the region that the two curves enclose. This curve is on the right. If it might be helpful if you rotate if you rotate this graph, which direction is this? If I rotate my graph clockwise, then I can actually see that really what I'm doing is we've just rotated the plane. Okay, and so if I rotate it, then it looks like a standard y as a function of x problem. And that kind of helps you see why this is, quote, the top function. The bottom function then is the function on the right, on the left. Yeah, the bottom function is on the left. So in this case, it is x equals 4y squared minus 12y. I actually forgot to label a couple points. So down here, this is the origin. I think that's clear. Up here, this is at y equals 3. Okay? That's where this top intersection point is. And so, whenever we're doing these things, whenever we're looking at this picture in the right-hand corner here of how we do things whenever we have y written as functions of x, the bounds are determined by the x values, right? Like this a and b represent x values. Here, our bounds will be the y values of the intersection points. Okay, so in this case, we can see that our lower bound is 0 and our upper bound is 3. All right? So let's go ahead and plug our stuff in. So we are going to integrate from 0 to 3. Remember, those are our bounds. Okay, our top function is, I'm going to put this 36y squared minus 12y cubed minus, now I'm going to plug in the other function, 4y squared minus 12y. And then all of that, we're going to put dy instead of dx. That's just because y is our variable here and not x. Okay. So let's see, this becomes the integral from 0 to 3. Looks like I'm going to have 32y squared. And then, or let me actually write it in descending order all the way. So I'm going to have a minus 12y cubed, then my plus 32y squared, then plus 12y, because I've got minus a negative, plus 12y, all of that dy. Now we're going to integrate, and this is going to be a fairly straightforward application of the power rule. So negative 12y to the 4th over 4 plus 32y cubed over 3 plus 12y squared over 2. And I want all of this from 0 to 3. Let's go ahead and do a quick bit of simplification. Negative 3y to the 4th plus, can't simplify this one at all, plus 6y squared, 0 to 3. But whenever I plug in 0, everything's going to go to 0, so I'm not really interested in what happens there. So let me see. If I plug in 3, I get negative 3 times 81 plus 32, oh boy, times 27 over 3 plus 6 times 9, negative 243. I know I'm going kind of quickly through this, but I trust that you can check me if you need to. 32 times 9 plus 288, and then plus 54. 240, that's going to be 40, that's going to be, I think, 99. I'm pretty sure. Come on, baby. Yes, well done, says my math lab. Excellent, excellent work. Okay, so I kind of went very quickly at the end here. This stuff is really all about the setup. Okay, so let me reiterate. Whenever we're trying to find the area between two curves, which are functions of y, we're going to take as kind of the upper function, the function which is further to the right, and the lower function as the function which is further to the left. Okay, when I say further to the right and further to the left, I mean over the given interval, over the region, over the region that they enclose, this yellow region. right? Like if I go far enough out, yes, this red graph will eventually go to the right of the blue graph. However, we're interested just in this yellow region. So that's how you determine which function is which. Then, rather than the x-coordinates of the x-coordinates of the intersection points, you bound the integral with the y-coordinates. And then from there, you just integrate. Okay? I shouldn't say you just integrate, because that makes it sound like, oh yeah, then you just integrate, and that's so... No. That isn't always easy. However, it's nothing new, right? This is stuff which we've been doing for a few days now. So that's why I didn't spend a ton of time on it. Problem 11 again asks for us to find the total area of the shaded this time of the shaded regions I think I will talk very briefly about how you would set this up, and then it will work very similarly to the previous. Find the total area of the shaded regions. Let me draw a nice picture again. Torn between trying to draw the picture quickly to save time and trying to draw the picture well and detailed enough. Okay, so we got one graph which is blue, and that goes like this. It goes like, okay, no pressure, Bailey. It's very steep. It crosses the origin here. And then it goes down, and that it's actually kind of symmetric. In fact, yeah, okay. So that is one region. Our second region, or a second curve rather, we don't have a region yet, it's just a line. There's no area there. The second curve is written in pink. I'll do it in red, because red's kind of like pink, right? I mean, sort of. It goes for like this. It goes through the origin, and then it kind of comes down like this. It's not as ugly as right there. I had a little, I don't know what happened. It's more smooth than that. But this point here of intersection is 2, -2. Oh, I'll also label them with the formulas in just a second. So this is 2, -2. Of course, we have the origin here. I hope that's clear. That's the origin, the big red one. And then down here, we have -2, -6. Okay, so this blue function is the function 3x squared minus, and I'm going to give it a name actually so that it's easier for me to talk about it. So blue is g of x, or f of x rather. Let's call this one f for totally arbitrary reasons. F of x equals 3x squared. Is that 3x cubed? Okay. 3x squared cubed minus 11 minus x squared minus 11x. And the red is minus x squared plus x, and I'm going to call you g of x. Oh boy, okay. Yeah, I'll talk through the setup here and then leave it to you to fill in the details. So here we have almost more, this is kind of more of a standard area problem in that we have y given as a function of x. So the general form is going to look something like the, well, actually that. So what I notice here is that I have to split up my region. I'm going to have to split this up into 2 regions and calculate 2 integrals. And here's why. Over the first, let me color these so I can refer to them by color. Okay, so I've got this yellow region, and then I've got a green region. Over the yellow region, so over the yellow, I see that f of x is going to be greater than g of x, right? The blue function is on top of the red function. Over the green region, we have it the other way. We have g of x is greater than f of x. So what I need to do then is I'm going to need to integrate both of these regions separately and add them up, because they need to be treated differently. So what I'm going to need to do, and I'll stick with the colors to be consistent so it's easy to follow. I'm going to integrate over the yellow region. Okay, so over the yellow region, my bounds of integration are going to be the two x values of the intersection points. So it looks like my lower bound is -2. Remember, here we're using x coordinates because we have y as a function of x. Okay, so be careful with that. This is what you'll most commonly see. What we did in the previous problem is less common. Okay, and the other bound it looks like is going to be 0 because it's the other intersection point is the origin. And since f of x is greater than g of x over this interval, it's going to look like f of x minus g of x dx. Now I need to add the area over the green region, the area contained in this green region. Well, here my lower bound is going to be 0 because the intersection point further to the left is x equals 0. And my upper bound is going to be 2. And here g of x is greater than f of x. So g of x minus f of x dx. And that's how you would get started. Then you'll do exactly what we did in the previous problem to solve. Okay? Okay, I'm going to take that. I will take your silence as a, I understand this perfectly. I'm of course kidding. It's okay if you don't. Okay. Finally, 13. They're going to make us do a bit more work here. I think, again, I'll get us started and show us how to set it up, and then leave it to you to fill in the final details. Find the area of the region enclosed by the functions. So here they are not going to give us a picture. By the functions. Okay, so my two functions, and I'm going to give them names. They call them y, they call them both y, but I'm going to give them names so that they're easier to talk about. So I'm going to call f of x, x to the 6th, and g of x, 8x cubed. So the first thing that you want to do, since we're not given a picture, is we're going to need to find the intersection points. So find the intersection points. How do you do that without a picture, Bailey? Well, we're going to set f of x equal to g of x and solve for x. Okay, and those will give us the x coordinates of our intersection points. So, if I have f of x equals g of x, well, that's just fancy talk for x to the 6th equals 8x cubed. Well, I noticed right away that x equals 0 is one solution. So x equals 0 is one solution. Now I'm going to divide both sides by x cubed, and I get x cubed equals 8. Which means that my other solution, if I take the cubed root of both sides, is x equals 2. Okay? So why don't we sketch a very quick picture here. Just enough to see what's going on the interval between them. So I've got x equals 0 here and x equals 2 here. So if I plug in, say, x equals 1, let's plug in 1 here and see what happens. Well, then f of x, I'll make f of x blue, and I'll make g of x red, or I just used red. I'll make g of x this golden-ish thing. So f of x, when I plug in x equals 1, I'm going to get just 1. Okay, so I don't know, it's like here-ish. I should put it in the color that I said I was going to put it in, shouldn't I? So this is f, so this is x, 1. Okay, and if I plug in x equals 0, well, at x equals 0, they're both 0. Okay, so they're going to look like, so they intersect. Oh, no, I want that to be blue now. And whenever I plug in x equals 2, 2 to the 6th, that's 64. It's perfectly fine if you do not know that. So this thing really blows up. Wow, okay, so it really is like, okay, it's like way up there. This is 64. So this is 264. Now if I plug x equals 1 into g of x, in fact, it keeps going. If I plug x equals 1 into g of x, then I get 8. Okay, so g of x is going to go like up here-ish. I know this is not to scale. But the point is that g of x is going to go like this. It's a cubic, so it looks something. It's going to start to shoot up like that. So this is my region that I'm interested in. And I can see that over my region now, I can see that g of x is greater than f of x. Oh, I said that I was going to make g of x gold, and then I didn't. Oh, no. Oh, no, 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 no. Okay, x cubed equals 8, and you're red. That's what I wanted to do. Okay, great. So this means that the integral, which I need to solve, well, again, my two intersection points, the x-coordinates are 0 and 2. And it looks like I'm going to have g of x minus f of x. G of x minus f of x dx. And I will leave it to you to take it from there to plug and chug and integrate and find this area. Whew, okay, I am tired. That was a lot of fun calculus. Time flies when you're having fun. I can't believe that it's almost been an hour and our time is almost up. If you have any questions, as always, please just let me know. I am here to help you, so please just communicate with me how I can do that. I hope that you find this helpful, and please ask questions if you have them before Monday's exam. I hope that you have a great weekend, and I hope that your exam on Monday goes absolutely swimmingly. Take care, and I will